So this is the first in a series of three lectures that I'm going to give in a recording setting in my Introduction to Computer Science course. And the lectures will be mostly in English with some Hebrew mixed in, excuse me, here and there. So the first lecture is about object-oriented programming, or in Hebrew, תכנות מונחי עצמים. And if we think about the course roadmap, so far we covered a lot of ground, but everything that we did was implemented or illustrated using what is known as procedural programming, or in Hebrew, or Hebrewish, תכנות פרוצדורלי. Well, now we are extending our tool set and beginning to talk about objects and about object-oriented programming. Now, there are many different ways to think about objects, and one of them is to view object as an extension of the notion of a data type. In Java, like in any other language, there is a fixed set of data types like int, char, double boolean, and so on. But the world around us is much richer and consists of an endless supply, so to speak, or an endless potential for defining and processing objects. Some of these objects can be concrete. Some objects can be abstract, some can be mathematical entities like fractions and matrices, some can be financial entities like bank accounts, and some objects can be game sessions, players, and so on. And in general, you can practically represent almost anything that you want using the notion of an object. So here are some examples that you see here in front of you. And during the course, we will discuss some of these examples. Let me say a few words just about one of them, big integer. In Java, there's a limit to the size of integer values that you can represent. And yet, in some applications, we want to be able to represent integers of any size. Well, we can do this if we create a new template for objects called big integer and use them in our programs. So as you see, this notion of objects is extremely useful. And if you want to be formal about it, any one of these objects is an example or an instance, or in Hebrew, dugma, or mofa, mem, vav, pei, ayin, of a general data type, and the data type is typically a set of, or is defined as a set of possible values. These values may be structured in the sense that they are actually buckets of values, or aggregates of values, and operations that I can perform on these values. So for example, matrices are, each matrix object is, you can think about it as a two-dimensional table. So these are the values that I can represent, and they are unlimited in terms of size. And there are all sorts of interesting operations that I may want to apply on these matrices. Now, the values that I just discussed are called objects. And object-oriented programming is the art of representing such objects and manipulating them in some clever and useful way. Now, in order to illustrate object-oriented programming, I'm going to use three examples: fractions, bank accounts, and two-dimensional points. And I do this because I want to illustrate the notion that you can use the same technology of object-oriented programming to work with many different animals, so to speak. A fraction is something which is very different than a bank account. So it's useful to see such very different examples. Now, whenever we talk about every one of these objects, we'll talk both about the abstraction of the object and its implementation. So let's begin with fractions. So we have this general notion or the concept of being a fraction, and we have an infinite number of possible fractions. A fraction in Hebrew is shever, 1/2, 3/7, and so on and so forth. Every one of these fractions is a pair of two integers. Now, in object-oriented programming, we call the template from which we generate these objects a class, and the objects themselves are called objects or instances of the class. And in instance, in Hebrew, is mofa, which is a very nice word in Hebrew. And an object in Hebrew is itzem. Now, the templates, once again, are the fraction in this example with capital F is the template from which I generate these objects. And in object-oriented programming, these templates are implemented as classes. They are very similar to the classes that we use so far, but they're also quite different, as you will see in a minute. Now, when we talk about the abstraction of an object, or in Hebrew, תיאור המופשט של עצם, we are talking about how to use the fraction objects in my programs. So, whenever I need to operate with or to do something with fractions, I can use these fraction objects. All I have to do in order to use these objects is have access to the API of the fraction class, and then I can do whatever I want with these objects. Now, the implementation of an object is something very different. Here we talk about how to build these classes, how to design and actually realize the fraction class, or the class that represents these objects. These are two very different views, and in this lecture, we'll begin with abstractions. So, here's an example of a typical dialogue. Bob says, I'm writing a program that needs to compute expressions like 1/2 plus 1/3, and so on. And I want to be very precise about these values. And that's something that Java doesn't know how to do, right? Java cannot represent fractions accurately. And so if you want to represent and operate on fractions accurately, you need to use something that looks like this. But Java does not provide it. Well, Alice, who is a very gifted programmer, says, lucky you. A while ago, I developed a class, which I called fraction with capital F, that enable people like you to create and manipulate such objects. And Bob says, great. How can I use these objects in my program? And Alice says, no problem. I'll give you my compiled fraction class, or if you want, I'll give you the source if you want to change it. But the compiled version is all that you need, and then you can import it into your code, as we will see later on, and use these objects whenever you need them. And Bob says, well, how will I know how to use the services of this class, especially if it's compiled and I don't have access to the source? How will I use these services? Alice says, well, I took the trouble of not only developing the class, I also wrote a detailed API, and I think that I did a good job doing it. You can access the API and use it as you please. So that's a typical setting of or in which objects come to play. Now, here is the abstraction, once again, or the API or the class skeleton, which are all the same thing in the case of fractions. Some things that I'm going to show you will look a little bit strange at first look, but they will become clear as we plow along. So here's the class fraction that represents signed fractions. They can have either a plus sign or a minus sign. And the API says that a fraction is characterized by a numerator and a denominator, מונה ומכנה. The first thing that we see in this class skeleton is what is known as a constructor. And a constructor is a special method that knows how to create new objects. So this constructor will create objects like 2/3 and 1/2, and how exactly to use it we will see in a minute. Then we see two methods called getNumerator and getDenominator that know how to return the numerator and the denominator of any given object, מונה ומכנה. Then we see some more interesting methods that do some arithmetic. So we have a method that knows how to add up two given fractions. We know how to multiply fractions, how to invert fractions, and there may be many other useful methods that we may want to operate on fractions. So this is the API. That's what Alice gives Bob. Now, designing such an API is an acquired skill, something that you learn from seeing many examples of well-designed classes. And these examples are sometimes called design patterns. And what we'll do now is we'll start explaining this API in more detail. So let's start with this notion of a constructor. Now, a constructor is a method that constructs and returns a new object, and it does it whenever someone calls it. And there is an object-oriented programming convention, which is that the name of the constructor method is always the name of the class in which this constructor is defined. So this constructor is called a fraction, just like the class. Now here's an example of using this constructor. I define two variables, a and b, of type fraction, which is now available to me. This is a new type. And I define two fractions, 2/5 or 2/5 and 4/8. Now take a look at the fraction constructor API. It says that it creates a reduced fraction. So if you ask it to create the fraction 4/8, it will reduce it to 1/2, always. Now, here is what will happen behind the scene when you run this client code. You will have two new variables, a and b, which point at two objects which are stored somewhere in the computer's memory. So what is the anatomy of this statement? Fraction a equals new fraction 2/5. Well, the word new is a reserved word in Java. And basically the client code calls the constructor, which is a method, remember, using the statement new class name. Actually, we call the constructor, which has the same name as the class name. Now, the constructor's code, which is not shown here, causes the operating system to allocate a free memory block for storing the new object's data. Here, the constructor will tell the operating system the user wants to create a fraction which consists of two integers. So go to the memory, find an available block of two words, and let's use it for representing this new object. Now, typically, after doing this, the constructor will typically do some object initialization work. Here we have a very good example. The constructor is going to reduce the object if necessary. And finally, the constructor is going to return the base address of the allocated memory block to the caller. And in a minute, we will see why this actually makes perfect sense. So, and indeed, the returned address, the address which was returned by the constructor, is stored in A, right? Because that's what we said. We said fraction A equals new fraction whatever. So as you see from the picture, now A points at the newly constructed object. Now, the API, thanks to Alice, hides all these implementation details from the caller. We sometimes call the caller the user of the fraction class, right? The user doesn't care about the operating system. The user doesn't care about how the initialization actually works. The user just wants to know that he or she can say, give me a new fraction, bye. That's the beauty of an API. You can use it without worrying about implementation details. Now let's talk about something new in this course, which is called object variables. A and B are two object variables. They are used to refer not to concrete data like 17 or 19, but rather they refer to objects, and as such, they contain memory addresses, just like array variables. So let's take this example a few steps further. Suppose that now the client code defines a primitive, a variable that has a primitive data type like int, x equals 17. Let's look at the memory. This is how this variable is going to be represented. And then suppose we say that we define a new variable y, which equals x, and the new object variable, fraction c, which equals b. What are we going to see in the memory? Well, what we're going to see is this, okay? Y will be a new primitive variable that contains the same value as x, but c, which contains a memory address, will contain the same memory address that b contains, and therefore effectively both b and c will point at the same object, in this case half. All right, and so when you compare primitive variables to object variables, both of them of course contain binary values, but the value of a primitive variable like x and y is interpreted as a data value, and at the same time the value of an object variable like a and b in this example is interpreted as an address in memory. And for this reason, object variables are yet another example of pointers or references, just like array variables that we already saw in this course. And indeed, in many different ways, objects and arrays are very similar, but objects are much more powerful than arrays, as we will soon see. Suppose I want to print an object. It's not obvious how to do it. So here again is my fraction class. Here is my constructor. And now we see something new. We have a function called toString, which is a special word in Java. This toString function returns a string. And the string is a textual representation of this fraction in the form of a numerator slash, or in Hebrew, lochsan denominator, moneh lochsan mechaneh. So that's what the API promises. The API says, I'm going to give you this textual representation of the current object. Well, so toString, by convention, it's the name of a method which is designed to return a textual representation of the current object. It's a very important debugging service, because if you write a program that creates fractions and manipulates them, I guess the first thing that you want to do is look at what you've done, right? You want to be able to display it on the screen or print it on paper or whatnot. So it's the responsibility of the class designer. In our story, it's our friend Alice, to write a toString method. She has to do it because client code or client programmers will expect to be able to use such a printing service. So here's an example of how to use it. We define two fractions, a and b, and then we write two statements. We say a equals plus or some string plus a dot toString. And then let's wait with the second statement and let's see what comes out. Well, the first statement generates a equals 2 over 5 because we called the toString method on the a object. And the a object contains or refers to the fraction 2/5. And indeed, we got 2 over 5 or 2/5, which is kind of nice. Now look at the second statement, which is much more succinct, or in Hebrew, metumtzat. In the second statement, we simply say b equals plus b. And we got the same thing, 1/2, which, look at this and say, how did this hocus pocus happen? Well, it happens by convention. In Java, when an object variable appears in the context of some string expression, as it does here, Java automatically invokes the toString method on this object, which is very nice. So whenever you want to print an object, you just give its name and the toString method will kick in and you will get a textual representation of this object. Very, very convenient. And now you see why it's the responsibility of the class designer to provide an implementation of toString, because it's so useful. All right. Another set of useful methods are called accessors and getters. And here are two examples of getters. These getter methods return the numerator and the denominator of the current object, which, is a very trivial and basic thing to expect. And so if we define a fraction, we can now say the numerator of a is a dot get numerator, and the denominator is a dot get denominator. And what we'll get is this output, which obviously is quite useful if you want to operate on fraction objects. So by convention, methods that give access to the object's data are called either accessors or getters. So here we see examples of two such getters. Now, once again, just like we said about toString, it's the responsibility of the class designer, Alice, in our story, to specify and develop or write these getter methods. Now, how many getter methods to define and how exactly to define them is a matter of product, so to speak. You have to ask yourself, what exactly am I supposed to do? I mean, someone should tell me what he or she wants to do with fraction objects. And if I will conclude that they need these accessors, I'm going to define them. So it's application specific. Different applications have different getters and setters, which is the next thing that we're going to see. All right, let's see some more examples of methods. But hold on, let me go back for a minute. Yeah, we didn't talk about setters yet. We'll talk about setters in a minute. And now we want to talk about some arithmetic methods. So we have the fraction class and the fraction constructor. And here is a very useful arithmetic operation. This operation returns the sum of the current object of the current fraction with another fraction. And multiply does the same, but does multiplication, and invert gives you the reciprocal or a shever hofchi of the current fraction, and you may have many more such fraction methods. Now, you may ask yourself, where is this fraction that I'm talking about all the time? Well, when I say the current fraction, I mean the fraction on which we are now operating. You will see in a minute what I mean by this. And in the world of object-oriented programming, the current object is always represented by a special object variable called this, THIS. And that's why I use this in the documentation. If you look at the API, look at ed, for example, it says returns the sum of this fraction, the current object, and the other one. Okay? Now, notice that methods operate or can operate on other objects, not only on the current object, and methods can also return objects as their return values. You see it from the definition of add, multiply, and invert. Now look at add, for example. Add receives as a parameter another fraction object, right? There is a variable or a parameter called other. The type of other is an object type, fraction, and add does something, and at the end, add is going to return a fraction object, which is the result of adding the current object and the other object. All right, let's see how we use these capabilities. So we define two fractions, a and b, and now we can say, I'm going to define a new object called sum, and sum equals a dot a of b, which we should read as apply the add method on the a object, and I'm going to pass to it b as a parameter. So when we say a dot add, it's like object name dot method name. We apply the method on the object. And when I do this, this a variable becomes the current object on which I operate. Okay? And then I can print the result. I can say a plus b equals sum. And what I'm going to get is this very nice output. So you see, I have a new way to work with fractions with very little effort, almost no effort. I can say 1/3 plus 1/2 equals 5/6. This is very accurate, and once again, this is a degree of accuracy that you don't get in Java, because Java doesn't know how to represent fractions. You need a fraction class to actually do it. So let's analyze this statement, sum equals a dot add b. First, we call the method a on the a object. This method is going to return a fraction object, as the API promises. And notice that this fraction object is going into the sum variable. So sum will now point to the address of the new object that add returned. Very elegant, I think. Very tight. Okay, another example of client code. I define 3 new fractions, and I want to compute a times b plus c. I do it in one statement. Fraction d equals a multiply open parentheses b add c, and then I print, I create some fancy printout, and I get this fancy result. Okay? Now notice, don't forget, there's a lot of work being done here behind the scene, because when I say print a plus whatever, it's basically a dot to string, right? Plus b dot to string, and so on. So the class, the fraction class, does a lot of work for me, and as a client programmer, I can use fractions in a very elegant way. The fraction class will carry the burden of realizing all these operations for me, behind the scene. Beautiful. Now, well-designed abstractions are designed to capture the requirements of the domain that they are trying to model. Or in Hebrew, כשאנחנו מפתחים איזושהי הפשטה או איזושהי מחלקה שצריכה לייצג איזשהו עולם ידע, אז אנחנו בונים את המחלקה הזאת בהתאם לדרישות של עולם הידע הזה. So, in the world of fractions, what is a fraction? A fraction in mathematics is the set of all the pairs, a and b, such that a and b are integers, and there are some operations defined on fractions, like add, multiply, invert, and so on. And the fraction set is closed under these operations. When we say that it's closed, it means that when you apply any one of these operations to two fractions, what you get as a result is yet another fraction. And this is captured very nicely by this class, because the fraction constructor is designed to take two integers and return a fraction type. And all the methods that we see here take one or more fractions and return yet another fraction. How do I know it? I look at the API. The data types of all these methods, of the return values of these methods, is fraction. So I realize these requirements. So let's look back at some of the ideas that we just learned. An object is an instance of a class. So 1/2, 2/3 are instances, or in Hebrew, mufa'im ba'ain, of the fraction class. Object and instance is exactly the same thing. Okay, so sometimes I will say object, sometimes I will say instance of the class. An object variable is a variable that refers to an object or to an instance, and it acts as the handle of the object, right? It doesn't matter how big or complicated this object is. It may be a matrix, it may be an image. I need somehow to hold it, right, in my hand. The object variable gives you this reference, this handle. Methods are functions that operate on the current object, which is unlike all the functions that we saw so far in this course, which had no notion of an object. Methods always operate on the current object. Constructors are special methods that create and return new objects. The toString method is a special method that returns a textual representation of objects. The only thing which is special about it is its name. If you use this name, Java knows how to plug it into string expressions when needed. Getters provide access to the object's data. So let's move from fractions to bank accounts, a very different animal. And yet, the object-oriented technology is going to represent it just as well. So once again, we begin with an abstract view of bank accounts, and we see both the template, or in Hebrew, a tavnit, from which we create bank accounts. This is the class called bank account. And we have instances or objects, or in Hebrew, atzamim or mofa'im, of the bank account class. And you see that every one of these objects is a collection of 3 values. First is something called ID, which is the number of this bank account, and it must be unique so that two bank accounts always have two different ID numbers. Then we see the owner of the bank account, which is simply the name of the person who owns this bank account, and the balance, which is in Hebrew היתרה, how much money we presently have in this bank account, which is a double value. Now, let me philosophize a little bit about it and try to think both about bank accounts and fractions, which are once again very different things. But you see, both bank accounts and fractions are examples of a more general thing, which is called an entity, or in Hebrew, yeshut, something that exists. It's like the most general thing, right? Something that exists out there. Now, you can think about an entity as a bundle of properties, or in Hebrew, ישות זה איזשהו אגרגט, או איזשהו, אני לא אוהב להשתמש במילה אוסף, כי באוסף אין סדר, ופה יש סדר, יש לי שלושה דברים שיש להם שלושה שמות שונים במקרה הזה. ישות של תכונות, שזה איזשהו אוסף של תכונות. So, the fraction entity consists of two properties, which are numerator and denominator. And the bank account entity consists of three properties, which are ID, owner, and balance. You see, every one of these things is a property of the bank account entity. I think it's useful to talk about it this way because when you talk about it this way, you see that fractions and bank accounts, even though they're so different, there are many similarities about them. And once you understand these similarities, you begin to understand better what is this notion of object-oriented programming. So the client view of an object is how to use these bank account objects in my programs. And the developer view, which we will see in the next lecture, not in this one, is how to actually implement, how to realize the bank account class. All right. So let's begin with the client view. Now, when we discussed the fraction example, we presented the fraction API as the usage contract, או החוזה שבעזרתו משתמשים בעצמים האלה, בעצמים מסוג שבר. Well, we'll now begin to discuss how developers actually design APIs. Not necessarily implement them, just the design, the architecture of the class. Now, when we design an API, when a software architect builds a class skeleton or class structure, he or she always starts by putting herself in the shoes, in the place of the people who will actually use the services of this class. So you have to ask yourself all sorts of questions. And the questions are, for example, what do we want to record about bank accounts? So obviously you need an account ID, an account owner, an account balance, but you may need many other different things, right? Like, for example, credit limit. I forgot how to say it in Hebrew. תקרת משיכה. How much are you allowed, to go into a minus in your bank account, or maybe the address of the account owner, or maybe whether this is a shekel account or a dollar account, and in a real bank account object, you may have something like 50 different such properties. And then you have to ask yourself, what do I want to do with bank accounts? Well, I want, obviously, to construct a new bank account, but I also want to perhaps display the the data of this account, deposit money, withdraw money, transfer money from one account to the other. So you see, when you design a bank account class, you have to think about all these possible functionalities, and this will guide you how to actually build this class. Okay, so let's see what we came up with. So here is my bank account class, which is designed to represent bank accounts. And notice the API says so. A bank account has an ID, which is an int. It has an owner, which is a string. It has a balance, which is a double. Very important information. There's no other way to know it. Now, here we have two, not one, but two constructors. The first constructor will get an owner and a balance and will create a bank account for this owner with this initial balance. The second constructor will do something similar. It will also create a new account with a new owner, and it will set the balance to 0. So we see that just like any other method, constructors can be overloaded. And then we'll have some financial functions or methods like deposit money into this bank account, the current bank account, withdraw money, transfer money from this bank account to another bank account. These are void methods. They don't return a value, but they do something very useful. Mm-hmm. And then we have some getters, get the ID of this bank account, get the owner, get the balance, and finally we have a toString method. In a typical bank account class, I may have dozens of such methods, but these methods are sufficiently good for generalizing to many more similar methods. All right, so as usual, let's take it one step at a time, and let's look at the constructors. I have this constructor, which operates on owners and balances and returns a new bank account. I have this constructor, and let's see how we use them. So Alice opens an account, and she begins by depositing 1,000 shekels. So here is the statement. I define a new object variable called AliceEc, and I call the constructor, passing the arguments Alice and 1,000. And then I print Alice account, and what I will get is the ID, which is 1. This is the first account in the bank, so it has ID number 1. I get the owner Alice and the balance 1,000. And then Bob opens the bank account. Unlike Alice, Bob doesn't specify an amount. We just say bank account Bob, and we print it, and we see that Bob deposited a 0 when he opened his bank account. So you see how useful it is to be able to have constructor overloading, because you allow your clients to create new objects in many different ways. In this case, in 2 different ways. So constructor overloading is very typical in object-oriented programming. You typically have several constructors, and they all have different signatures, and that's how the compiler knows which constructor we are talking about. Also, we see another nice example of using toString, right? Because when we want to see an account, we simply give the name of the object variable, and somehow we get all this useful information: ID, owner name, balance. How does this hocus pocus happens? Well, apparently there is a toString method somewhere here which we haven't seen yet. So we'll see it in a minute. We saw the 2 constructors. Here we see some getters: get ID, get owner, get balance. And when we use them, here I define a new constructor, and I define a new bank account, and I say, let's see what is the current balance of Ben. So I simply say Ben account, which is an object variable, get balance. And I get a number like 5,000. So getBalance is a method which always operates on the current object, and the current object in this case is Ben account, B-E-N-A-C-C. So clients access the object data by using accessor methods, and that's why these methods are called accessors or getters, which is the same thing. Now, what about setters? Okay, well, let's see. So I have the constructors and the other methods, and I have this deposit method and the withdraw method and the transfer to. And I see that these methods actually change the state of the object, right? The state of the object, when I say the state of the object, or in Hebrew, matzav haobjekt, the state of the object is the current values of this object, which are ID, owner, and balance. Every method that messes up with these properties is called a mutator, a method that changes the state of the object. Now, in the case of fractions, we didn't have such methods. We had methods like add, multiply, and so on, but these methods, if you recall, didn't touch the current object. They always returned a new object, right? These methods are very different. These methods operate on the current object. In bank account, we want to do it because that's the nature of bank accounts, right? They have a balance which keeps on changing. So we call them either setters or mutators because they mutate, which in English is a synonym for change. They change the object. There's no need to change fractions. You see, a fraction, like 1/2, is 1/2, is 1/2, is 1/2. You don't want 1/2 to become 1/3. It's crazy, right? And therefore, when we built the fraction class, we didn't write any mutators. But when we write the bank account class, we need mutators. So once again, the architecture of the class reflects the application. You know, it's not something that you do in a vacuum. You always do it in a certain context. So whether it's mutable or immutable, it's decided by the class architect based on the requirements of the application. All right, so far, here is the condensed API, API המתומצת. We have a class called bank account. We have constructors. We have deposit, withdraw, and transfer. And let's start to use it. So Alice creates a bank account, and so does Bob. And then we print these two bank accounts, and we get that Alice has 1,000 and Bob has 0. And then, let's read it very carefully. Alice withdraws 200. Bob deposits 500. Let's print again these two object variables, and we see that Alice began with 1,000. Now she has 500. And Bob began with 0, and now he has 500. And then let's transfer some money from Alice to Bob. So look at the syntax. Alice, transfer to Bob, 400. And now let's look at the balances of Alice and Bob. We print it. We see that Alice has 400 and Bob has 900. So the transfer worked perfectly well. So, and by the way, just as a comment, you know, in this application or in this example, we don't do any data validation. We don't check if you went beyond your credit line. We don't check if you enter valid values. Obviously, you can do it. You can do it something called exceptions, which is a Java feature that we haven't learned yet in the course. We'll learn it later on. If you want to do data validation, obviously in real life you want to do it, you will have to document it in the API. But in this example, we don't do it. But notice how elegant the syntax is, right? We created a little language, a little financial language for depositing, withdrawing, transferring money, and everything is very readable, very easy to understand what's going on. And that's the beauty of object-oriented programming. It enables you to model the world in a very elegant way. So this is the bank account example. And with that, let's move on and talk about our last example for this lecture, the point class. Well, a point is actually a pair of two double values, as you see from this slide here, right? Here's the point class, and here are the objects or the instances of the point class. And the client view, as usual, is the abstraction, which is how to use point objects in my programs, and the class view is the implementation, how to build the point class or the point type, if you will. And as usual, we are going to talk about the client view because the class view is something that we are going to discuss in the next lecture. All right, so here's the API of my point class. It represents a point in a plane, and I should have said in the API, and I regret that I didn't do it, I should have said a point is characterized by two coordinates which are two int values. Something like this. I should have said it. All right, so I said it now. But obviously it should be part of the API. You can also figure it out, by the way, from the constructor API. And indeed, the constructor, which constructs a point, as you see, it takes two parameters, two double values, x and y, and it returns a new point. The toString method returns the textual representation of a point as the values x and y separated with a comma and enclosed with two parentheses. This is not obvious. You have to actually say it, and next week we're going to actually build it, make it happen. And then whoever asked me to do this class, he or she requested that we also have a Euclidean distance method that computes the distance between this point and another point. This is a double. It's a double value. And just like we had with fractions, we can also add points. But this is a vector addition. When you add a point to another point, what do you get? Yet another point. So the add method is going to return a point. We can draw draw a point, which is kind of interesting. It's not obvious. So we can actually draw a point on the canvas. And we can also draw a line from this point to another point. And we can add many more methods just, as the application requires. There's a whole story here which we don't have time to tell, and I didn't even make up the story, but I assume that someone wants us to create this point class, and we are operating in a certain context based on the requirements of the application. So that's kind of a side story that you have to keep in your mind. Here's some examples of client code. We create 2 points, and then we say P1 plus P2 equals P1 dot add P2, right? We apply, or here's another nice word in English, we invoke the add method on the P1 object. So to invoke a method is like calling a method. And we pass P2 as a parameter. So what we're going to get is a new point, which is the result of the vector addition of P1 and P2. P1 will be the current object. P2 will be the other object that we're going to add to P1. And the output of this code is going to be a point plus another point equals a third point. And as you see, I get a lot of action with very little code, right? And I get all this goodies because the class knows how to do it. And the client programmer can use these points without worrying at all about how all this functionality is actually implemented, which is fantastic. You have to understand what we're doing here, okay? This is a very nice example of modularity. The user or the client has lots of problems of his or her own. And as part of solving these problems, he has to use points, two-dimensional points. So he's very lucky that he doesn't have to worry about how points are actually being realized. There's someone else worries about that, right? There's someone else is the point class. So that's how you manage complexity. You separate your challenges or your problems into modules, and you handle each module separately. All right, so here's more examples of client code. I created 2 points, and then I say draw these 2 points, and then draw a line from P1 to P2. These method invocations, this method calling is going to open a standard canvas, and I will see the 2 points and a line drawn between these 2 points, which is kind of nice. So obviously, the point class is going to use the services of std draw. Also notice that the draw method and the drawLine method are void. And because they are void, I can simply call them. You know, I don't have to assign a value to a variable like we did with the fraction and actually only in the fraction class. In bank account, deposit, withdraw, and so on were also void methods, I think. All right. Here's some more example of client code. Now we want to create and draw random points in a two-dimensional plane, which is defined here. So notice what I'm going to do. I'm building an array of point objects. The name of the array, I decided, is going to be points with lowercase p. That's the name of a variable. But the data type of each one of the elements of this array is going to be a point object. And I'm going to create 100 such points. And then I'm going to build these 100 points by using a for loop. The for loop goes from 0 to 99. And for every one of these values, I don't really use the I value. I use the I only to stage the loop. I do use the I value. The I is actually the index of the array. So points in location I equals whatever the constructor will return, right? The constructor will get 2 random ints, and random gives me a number from 0 to 1, so this is kind of convenient. So the constructor will create a random fraction. It will put it in memory, and the address of this memory block will go into points in location I. And I will do this 100 times. So this piece of code here creates 100 random objects. And then I'm going to draw all of them. So another for loop, and I go through every one of the array elements and I draw it. So basically I call the draw method on every one of the points I elements, and every one of these elements is a point object. So everything is very well defined. And what I'll get is something that looks like this. Now, as usual, I'm giving you the code. You can play with this. You can create an array of 1,000 or 100,000 random fractions. This is another nice way to check the validity of Java's math random. If you will ask it to create, let's say, 100,000 objects, random points, I would expect to see a blackened canvas with no holes, or maybe a few holes, but the holes should be kind of random. So, you know, the more random it is, the more good will be the coverage of this space here. So let's begin to wrap up this lecture and make some observations. Point is a new type. It does not exist in Java. We basically added it to the language. It is as if we extended the basic language with a new type. And we can do it just like we can create arrays of primitive data types, just like we can do, just like we create arrays of. So let's begin to wrap up this lecture and make some observations. Java does not have a point data type. But once we created this class, it's as if we have a new data point. We have a new data type, right? We can use this data type in our programs. We extended the language in a very useful way. Now, not only we can create individual objects, we can create arrays of such objects, right? And in this case, we created an array called point. Now, this capability actually is going to be very useful in the next homework that I'm now writing. In homework 9, you're going to use an array of objects for doing something quite surprising. Here's some more observations. The point class basically gives us a new way for talking about and operating on two-dimensional points. And I can use this language, so to speak, without knowing anything about the point class implementation. All I need is the API, right? If I have the API, I know how to invoke the methods. I know how to call these methods. I can make my programs sing and dance with point objects, okay? And if the API is well designed and well documented, it will be very easy to write client code that creates and manipulates objects. If the APIs and the class are badly designed, as very often happens, it will be a nightmare to use the services of this class. So class architects are extremely important. You know, if a class architect knows what she's doing, she's going to save a lot of trouble to numerous programmers who are going to use this class. How to build all these classes, how to build the fraction class and the bank account class and the point class. That's what we'll do in the next lecture next week. See you then.